welcome back, and today we're going to take a look at some vacuum tubes. Most notably, we're going to take a look at one of these. And don't be surprised if you can't see at all what I'm holding. It is tiny. This is a neon bulb, and it may seem weird for me to say vacuum tubes and then hold up a neon bulb. And also, why are we taking a look at just a neon bulb? It's just an indicator, right? There's nothing really all that special or unique about these, right? Wrong! Neons are awesome! I love neon bulbs. They can do so many things, so much more beyond just a simple little indicator. So we're gonna try and explore some of those today. So, well, I've got this one right here, but I have a bunch more on the bench. So let's hop over to the bench and take a look at what these things can do. Also, I want to give you a little bit of comparison of just how tiny this thing is because it is minuscule. So let's hop over there and get started. All right, let's start with a bit of a size comparison. This is a VT154, or I think it's equivalent to an 814. It is a power pentode, and it is the physically largest vacuum tube that I have. This is a 6080, and it's quite a popular power dual triode. And this is an octal base, and they are also quite large. This one is a 6CG7. It is a 9-pin base, or a novel tube, and it is also a dual triode. And now we're getting down to what is classed as a miniature tube. Well, you can see it's pretty small compared to the others. And then moving one step even smaller, this is a 2D21. It is a 7-pin base, or a heptal tube, and this one is a thyratron. And then getting even smaller than that, this is an MTX90, and that's all I'm going to say about that one for now. And anything smaller than that, we get into the class of sub-miniature tubes. This is a 6021. It is a dual triode, so comparatively it is absolutely minuscule. And then the last hurrah of vacuum tubes was this little guy right here. This is a 7586 New Vistor, which is a single triode. And even though it's in a metal case, that is indeed a vacuum tube. And finally, here is our tiny little neon bulb. So you can see that when I say these neons are small, they are positively tiny. And so what exactly is a neon, and what makes me love them so much? Well, we need to look at some documentation to fully understand what's going on inside. Now, earlier I called neon bulbs vacuum tubes, and that seems weird. A neon bulb is filled with neon gas, therefore it can't be a vacuum tube, right? Well, yes, a neon bulb is filled with neon gas. It's about 99.5% neon gas, and then there's about 0.5% of argon in there. And sometimes, depending on the type of neon bulb that you buy, there might be just a splash of radioactive material in there to help the neon ignite in extremely dark conditions. This is something that's called the dark effect, and that is that if a neon is stuffed in a place where absolutely no sunlight can get to it, sometimes the gas in there has a hard time breaking down. So a little bit of radioactive material provides just enough impetus to get that gas to start breaking down. But it's important to note that the combination of all of those gases inside of that little glass bulb is at an extremely low pressure, about 1 to 20 torrs, and torrs is a weird unit of measure that I'm not used to. So if we change it over to say something like kilopascals, it's about 0.1 to 2.5 kilopascals hiding out in there. To give a little bit of reference, the atmospheric pressure of the Earth is at 100 kilopascals. So to put that into freedom units, that's 14.7 pounds per square inch is our atmospheric pressure, which means that the pressure inside our little neon bulb is on the order of 0.02 to 0.4 psi. It is very nearly a complete vacuum. Now, a neon bulb only has 2 leads, and if we look really close inside the gas, you can see that the 2 electrodes in there don't actually touch each other. They're completely electrically separated. So how do we get our glow? Well, it's actually incredibly similar to the mercury vapor rectifier that we took a look at a few weeks back. We're relying on something called Townsend discharge. This is the idea that if we put a high enough potential between these two electrodes, the gas that is floating in between them starts to ionize. And when it ionizes, it creates a conduit of plasma between the two electrodes, essentially connecting them and giving a path for the electrons to flow. And it happens at a very specific voltage in neons, and that's the breakdown voltage. Now that voltage can change pretty wildly depending on the pressure of the neon inside the tube. Higher pressures means a higher breakdown voltage. It can also change depending on what other gases are mixed in there. How much argon are we mixing in? That can really affect the breakdown. And the neons that we're looking at today actually have a breakdown voltage of around 90 volts DC. Now once that breakdown voltage is hit and the gas starts to ionize, that's where we see our glow. Now because of physics, we only see the glow around the cathode. Also, neons are ambiguous. The cathode can be either electrode and the anode can be either electrode. And this can actually be used to your advantage by sending a differential voltage either one way across it or the other way across it. Notably, the HP521A frequency counter, or more importantly, the AC4 decade counters inside of it, use this principle, the idea that you can send voltage either way through a neon and it will illuminate. But all of this is just talking about how we get that glow. That doesn't explain why I'm so fascinated with neons. And well, that actually happens when we take a look at the current through the lamp, because the breakdown voltage and the maintaining voltage are different. So if we look at this little graph right here, we can see that the current through the lamp is essentially nothing at low voltage. But as our voltage increases, we eventually get to point A here, and that's where Townsend discharge starts. And then between B and C, we have the breakdown of that gas, creating that ionization. And as that happens, the current through the lamp increases. Now, once we get to C to D, we hit a transitional stage that brings it down into normal operation. But it's important to note here that the current through the lamp has increased, but the voltage has decreased, which means that it experiences a sort of negative resistance. The amount of resistance through it suddenly decreases. So while in this example we need 110 volts to get to breakdown voltage, once the neon lamp is illuminated, we only need about 80 volts to keep it illuminated. So we have a 30 volt space in the middle there where the voltage can be whatever it wants and the neon will stay illuminated. And then if we want to extinguish the neon lamp, we have to drop it below 80 volts. This is a form of hysteresis, that striking voltage versus that maintaining voltage. And the difference between them we can exploit to do some really unique stuff. But when I say unique stuff, that doesn't really tell you what exactly we can do with neons. Well, just as an example, we of course can use them as indicators, but you can also use them as voltage regulators, as a voltage reference, as a relaxation oscillator, as all of the kinds of multivibrators. You can make logic and logic OR gates out of them. You can make ring counters, you can make decade counters, you can make trigger circuits. Neons are amazing because they're essentially the Swiss Army knife of electronic components. They can be used in almost any situation. But I am mostly interested in using neons for building computing circuits, because some of the circuits that I build with vacuum tubes could be greatly miniaturized with neons, which I think is fantastic because they're also still vacuum tubes. So I've got some circuits on the breadboard, so we'll pull that out and take a look at some stuff that I thought was really interesting. All right, I've got three simple neon circuits on the breadboard here, and for the B+ voltage, I'm using 150 volts, and I'm using one of those cheap boosters that you can get on Amazon. Now, neons use such incredibly low current that you can generate the high voltage required for neons in many different ways. Now, it is important to note that there is 150 volts on this breadboard, even if it is at incredibly low current. It is Not enough to kill you, but it is enough to wake you up. Ask me how I know. So if you're going to do this at home, be careful with it. It's 150 volts. The first circuit that I want to take a look at is just a simple indicator circuit. We have a 220,000 ohm resistor coming off of 150 volts, goes into one pin of our neon bulb here. The second pin goes through a push button to ground. So if I push the push button, yeah, the neon lights up. That is an indicator circuit. That's really cool. Now the next circuit I want to take a look at is an astable multivibrator. So we essentially take two neon lamps, we take the anodes and we connect them to each other through a capacitor. In this case I'm using a 4.7 microfarad. And then we have two big resistors that go to B+. In this case, I'm using 1 mega ohms, and then we have the cathodes of each one going through a 10,000 ohm resistor to ground. Now, I put a little switch between ground and those 10,000 ohm resistors so I could turn it on and off. So if I flip this little switch here, yeah, there we go. Check it out. We've got our little astable multivibrator going on. We essentially built ourselves an oscillator. Now, an important thing to note here is that the cathode of each neon goes through a separate 10,000 ohm resistor to ground. If we couple the cathodes to each other and then we change up the resistor values, we can essentially change this over to being a bistable multivibrator, which is exactly what this third circuit is. We have 100,000 ohm resistors coming in on the anodes, and then again we have the same 4.7 microfarad capacitor coupling the anodes to each other. The cathodes are tied directly to each other, and then there's a 470K to ground. Now this cathode resistor has to be quite large because a certain amount of voltage drop has to occur across it in order to prevent the circuit from going into a free running mode, essentially becoming an astable multivibrator. And again, I added a little switch on the bottom here so I can actually flip that switch to turn it on, and you can see that just one neon is staying illuminated. Now, coming off of the anode of each neon, I have a little push button that goes to ground. So if I push that push button, it will ground out that anode, which will change the state of the multivibrator. And then we can push the other button to send it back. So essentially we have a set, reset, flip-flop. We've built essentially one bit of computer memory out of neon bulbs. We just set and reset, 0, 1, 0, 1. That's awesome. Now the next obvious question is, this little astable multivibrator's been sitting over here blinking its heart out for a little bit, but what does the waveform on that look like? And well, at such a low frequency, it's going to be really difficult to see. So we need to speed the frequency up, and then we need to hook up an oscilloscope so we can get a look at that waveform. All right, I've got my HP 150A scope out here, full vacuum tube oscilloscope, very, very cool. I've got the scope probe hooked up to the anode of one of the neons in our astable multivibrator. I switched out the capacitor with one that's much smaller so we could actually see it on the scope here. Now, it's not the most stable of waveforms. You can see that my trigger here is going a little bananas with it, but essentially that's what the voltage on the anode of our oscillator looks like. Now, that's kind of a strange looking waveform, but we can actually see some really interesting stuff here. The long, smooth path that goes up that looks almost like a sawtooth, that's the capacitor charging up. And once it gets to a certain point, it ignites and discharges down to a set level. That's very cool. But what's even more interesting is if we change the scope probe over to the cathode of our multivibrator here. So I'll go ahead and just pull it off of there, connect it up to the cathode here. Now the voltage level is going to be much lower because we're on the cathode at this point. And yeah, look at that. We have the same instability. Also, my scope probe isn't getting a perfect connection here, but look at that. It's a square wave, essentially. Now we're set to 0.1 volts per division, but I'm in times 10 mode. So that's going to be 10, 20 volts. We essentially have a 20 volt square wave being produced by our astable multivibrator for our neons. How cool is that? So we were able to make an astable multivibrator and a bistable multivibrator. But only having two pins in a neon feels kind of limiting at times. It sure would be nice if we could slip a little control grid in between the anode and cathode of our neon tube and essentially have a full-on neon vacuum tube triode. And if you remember all the way back at the beginning, I showed an MTX90, and that is exactly what this is. All right, let's just give this a real quick test. I've got an MTX90 set up on the left here, and the illumination actually comes out of the top, so that's why we're elevated a little bit so we can look down into it. Going into the anode of the MTX90, I have a 220 kilo ohm resistor, and then the grid, I have a 1 mega ohm pulling it to ground to hold it low, and then I have a push button with a 100,000 ohm to 150 volts to pull it high. This is very similar to how I would set up a normal triode. So let's push the button and see what happens. Yeah, there we go. We can see that it is illuminated. Now, if I release the button, it stays illuminated. That is very interesting because even if I press the button, the brightness does change, but it never actually turns off. It stays conducting. So it's not like a conventional triode. That's really interesting. I think we're going to need to take a look at the datasheet. So here is the MTX90 and the Russian datasheet for it. But first things first, my good buddy Gerrit hooked me up with a box of these. He's an absolute legend, and he's actually trying to learn how to make new neons himself, which I think is really, really cool, and I'm really rooting for him because if he can make me some really unique neons, I think we can build some really cool computing circuits with it. But he's also creating a vlog of his trials and tribulations, so if you're interested in seeing some of his successes and failures, there is a link down below. But these MTX90s are really interesting. Now, obviously I can't read any of the data sheet, but the important bit to notice is this little illustration at the top. First thing, it points out where pin 1 is with a little black dot on the outside of the glass case, which we can see right here. The next important thing to note here is that the anode and the cathode are not interchangeable, but just like a neon, it is a cold cathode tube, so there is no heater in here. And so the cathode is pin 1, the anode is pin 2, and pin 3 is our control grid. Now in our example, we put 150 volts on the anode and it didn't illuminate until we took the control grid high. So we were controlling the flow of electrons through the tube. However, once the gas ionized, our control grid was essentially made superfluous. And I think we can classify this as a feature, not a bug, because this is actually a thyratron. It's a cold cathode thyratron. It's actually very similar in operation to this 2D21 that we took a look at earlier. Now the 2D21 is not a cold cathode thyratron. There is a heater in there that heats the cathode up. It's also not filled with neon. I think it's filled with xenon? However, the operation is the same. Once we bring the control grid up to a high enough potential to allow enough electrons to flow through the tube to ionize the gas, the plasma encases the grid in a sheath of positive ions, essentially eliminating it from the circuit. Which means that the only way to de-ionize the tube is to cut off the flow of electrons from anode to cathode. Now, another big difference here though is that the MTX90 is not going to be able to move nearly as much current as the 2D21. But now that we know how it works, I think we can figure out how to turn our MTX90 off that's sitting over there still illuminated. So we now know that the MTX90 is a thyratron, which means that we can ignite it using the grid, but once it's ignited, we have to interrupt the flow of electrons from anode to cathode. And well, the easiest way I can think of doing that is to connect the anode directly to ground. So I've got an extra little push button here that does exactly that. So we'll just go ahead and pop that in place. And then if I push the button, yeah, check that out. We extinguished our MTX90, and then we can reignite it by pushing the button on the grid, and we can extinguish it, ignite, extinguish. That is awesome. We have created a set reset latch. Set, reset, set, reset. 1, 0, 1, 0. We created another 1 bit of vacuum tube memory based on neon gas. How cool is that? But if we can make a bistable multivibrator we should definitely be able to make an astable multivibrator as well. And that's what this second MTX90 over here is doing. Essentially, we have a 470,000 ohm resistor coming from 150 volts into the anode. And then we have a 1 mega ohm resistor connecting the anode to the grid. And we also have a 4.7 microfarad capacitor connecting the anode to ground. And then coming off of the cathode, we have a 10,000 ohm resistor. So this little switch here is just disconnecting the cathode from the rest of the circuit. So if I flip that, it should start oscillating. And yeah, check that out. We've got an astable multivibrator going on here. That is really cool. But I'm also really curious what the waveform looks like coming out of this thing. All right, I've got the HP150A scope hooked back up, and this time we're reading directly off of the cathode of the MTX90. I swapped out the capacitor with one that was a little bit smaller so we would have a faster oscillation. And well, you can see it's got the same problem that the neons have, and that it's really causing the trigger to go a little ballistic here. But this is a very interesting waveform that we're seeing on the cathode. The big flat spots here I'm thinking are going to be ground essentially, and then we have massive spikes up. Now that's not a very useful oscillator, but I think we can get a better looking waveform if we go off of the anode. So let me disconnect the scope probe here. We'll swing it right over here and connect it up to the anode. And yeah, look at that, an almost perfect sawtooth waveform, except for the fact that it goes a little nutso over on the far right there. Man, I just can't get the trigger to play happily with it. And you know what? That might just be an artifact of using neons as astable multivibrators. Or probably more importantly, my resistor sizes and capacitor sizes are just not good. But the result is astounding. We were able to build both an astable multivibrator and a bistable multivibrator using minimal parts with both an MTX90 and a neon bulb. And I'm only just scratching the surface of what you can do with neons. So hopefully I sparked a little bit of interest in the MTX90 thyratron, as well as just regular old neon bulbs in you guys, because I find these things absolutely fascinating. As I said before, I think they're the Swiss Army knives of electronic components. You can use them for just a ton of stuff. But I'm going to keep thinking of interesting computing circuits that I can build with these, particularly these MTX90 thyratrons, because I think they are beautiful. So I want to thank you guys so much for watching, and I hope to see you in the next episode.